Hi Rockridge, this is Mrs. Berger, and for Unit 7, Day 3, we will be discussing curves of best fit. And curves of best fit relate to when we have a set of data points, of discrete data points, so individual data points, as opposed to continuous functions. So we've got discrete data points that are usually shown on a scatter plot. You've probably seen scatter plots before. And we try to fit a model to that data. Okay. This model is so that it serves a purpose, right? It's so that we can try to understand or assess the past and or help predict the future, okay? Or try to understand what would happen within the bounds of the experiment we ran or outside the bounds of the experiment that we ran. For every scenario, the behavior of the data is different, and therefore we need to have some tools to help us decide the best model. So we're going to talk about three tools that we always use. The first one being the statistics capabilities of our calculator. We will put in the statistics that we've collected from our experiment, and we'll let the calculator display them for us on a scatter plot and then help us fit a curve to them. So on your calculator, I'll walk through this, but these notes here are just for your reference when you're trying to do this on your own. Before you start, we want to make sure that you have stat diagnostics turned on. And we want to make sure that stat plot is on. And so those instructions are there. I'll show you that in a second on the calculator. And then I'll show you how to enter the data in the stat menu. And then I'll show you how to zoom to actually look into and look at the data itself. Once we look at the data on the scatter plot, we will then be a little bit more informed to see the data and figure out which model would best fit it. So I'll show you those steps on the calculator in a moment when I actually have real data to look at. But I also want to talk about tool number 2. Tool number 2 is something that the calculator will feed us, and that's called the coefficient of determination, or R-squared. The coefficient of determination helps us determine if the model is accurate, or how inaccurate it is, or if it varies too much from the given data points that we wouldn't want to use that particular model. Okay? The values of R-squared are always going to be between 0 and 1. The closer R-squared is to 1, the better the model. Okay? So if R-squared is exactly 1, the model is a perfect fit, and that model accounts for 100% of the variability in the data. R-squared is what's going to be listed underneath your regression model when you run it in stat calc, and the reason we turn stat diagnostics on is so that that R-squared value does pop up when we do stat calc. Okay, so again, I'll show you that when we run it. And then our third tool is our common sense, and I know that sounds a little flippant and silly, but when you look at the data and you look at the scenario that the data was taken from, that will help inform you as to which model you might want to use. So for instance, if you think about the sale of rotary telephones from 1980 to 2018, you wouldn't expect that to be a climbing model of any kind. You would not expect that to be an exponential growth model, certainly. Rotary telephones clearly should have gone down in a downward trend. So we would expect maybe a negative exponential or a negative linear or maybe even a negative logarithmic, but certainly not positive exponential or a quadratic. In nature, growth of bacteria or radioactive decay or even business growth like economics, you would probably see those modeled with an exponential. Exponential growth or decay, exponential growth of bacteria or exponential decay of radioactive material, you would expect those to run exponentially, but probably not linear or quadratic, right? You don't see radioactive material go down and then go back up again, right, like a quadratic. So again, when you look at the scenario of radioactive decaying material, you use your common sense. That's probably going to follow an exponential decay, not a quadratic. Or things that are being impacted by gravity, a projectile that's been kicked, a ball that's been kicked or thrown or shot in the air is almost always going to be, looking like this, right? Because of gravity, it's almost always going to be a negative quadratic. And so that's the model you would likely gravitate towards, within your calculator. But probably not anything else, right? I really don't think any other projectiles are going to follow. Unless you're on the moon or someplace else, I don't think you're going to follow a different model. Okay? So using those three things, we are going to go investigate our first example here. Oh, I lied, sorry. We're going to take a look at some examples here where somebody has plotted some data, and you plotted that data in your calculator, and you hit zoom 9, and you're looking at these scatter plots, and you're trying to make a determination about which model you'll choose. If you were to look at the leftmost model, think about which model you would choose in the calculator. This looks like an exponential decay. And so you would pick expreg for exponential regression in the calculator. Okay? The second one, if you saw data that looked like this, or a scatter plot that looked like this, you would choose quadratic, which is under under quadreg on your calculator. If you saw this one, you most likely won't see it. You would map a cubic, and so you'd pick cubic reg. You really won't see those in this class. And then if you saw data that looked like this is actually an exponential decay. It's an exponential growth, unlike the first one, which was an exponential decay. So this one's an exponential growth. And once again, you'll choose expreg as the model on your calculator. Now, one last little piece of information before we take a look at an example. We want to look at interpolation versus extrapolation. So once we're done fitting a model to these scatter plots, like I said in the beginning, we don't just stop by fitting a model there. We use that model to understand something that we haven't measured exactly, right? And so if we are trying to figure out a predicted value that is within the original bounds of the data set, so within the bounds of the original data set. So for this quadratic here, if we want to know, so let's say that this value right here is when x is 0. What if this value right here is when x is 2, and you wanted to know what the output value is for when x is 1? We didn't actually collect an original piece of data at x equal 1. And so we will use our perfectly fit model, or our really good model, to tell us what the prediction is at that point. When we have that within the bounds of the original data set, that's called interpolation. Interpolation. It's within the bounds of the original data set that we're trying to use for prediction purposes. When we want to know something outside the bounds, so if we wanted a value that was outside the original bounds of the data, either below or above, if we wanted to know what the prediction is here or here outside the original data set, that's called extrapolation. So that's outside the bounds of the original data set. Okay, so extrapolation, interpolation. Interpolation is when you're trying to predict the value within the original data set. Extrapolation is when it's outside. And typically we trust interpolations more than extrapolations, especially if we are extrapolating really far from the original data set. We really don't trust really far out extrapolations near as much as we would trust an interpolation for when we're trying to predict values. Okay? Alright, all of that background, let's get into an example. So this first one, we're going to stay simple. We're going to stick with line of best fit. You've probably already seen these in the past. So we're taking a look at a rule that anthropologists use when they dig up bones and they notice that a femur is of a certain length. They can predict how tall the person probably was. And so they've collected data of femur lengths versus height. These are actual data points, and we'll put these data points into our calculator and then try to make some predictions. So let's go look at our calculator. Okay, on our calculator, remember what I first said. Make sure that in the mode menu, you come down to Stat Diagnostics, and turn those on. So enter over top of the on. And quit out of that. And then go into second y equals for stat plot. And you can either turn them all on or turn one of them on, as long as one of them is on. That way we'll see our scatter plot. Then to enter our data for the femur length and the height, go to Stat, Edit, and enter your data. So in list 1, I put all of the femur lengths, and in list 2, I put all of the heights. And take a moment to make sure that you've entered them correctly. You can definitely throw off your entire answers if you've accidentally typed something wrong into the calculator. So when we look at this data, hit zoom 9 for zoom stats, and it'll zoom straight to where your data is. And as you can see, this looks pretty linear. So once you've looked at the data and thought about it, with your common sense of what this model probably is, determine that you need a linear model to fit this, and go back to Stat, go over to Calc, and look at all of your choices. You've got linear regression, quadratic regression, cubic, quartic, another type of linear that you use more in statistics, natural log regression. You've also got exponential regression down towards the bottom, as well as logistic. You've got some other things that you won't probably use in this class. So typically we'll be looking at either exponential or quadratic regression, but we are walking before we were running today, so we will look at the linear because we saw that it pretty much followed a line. So linear regression, you'll be taking your x's from list 1, your y's from list 2, those are defaults, and we're going to go on down to calculate and hit enter until it calculates it for us. So what this is telling you is the line of best fit is going to be of the form y equals ax plus b, and for your data, the a is 1.923, the b is 80.681, and this is a pretty good fit. Your r squared value is close to 1, right? It's 0.93, so it's accounting for 93% of the variability in the data. This is a pretty good model. We like it, and we will use it in our answers for this question. So the equation is going to be y equals 1.923x plus 80.681. Our coefficient of determination is 0.933. That's a good fit. And so using that equation, if an anthropologist finds a femur length of 58 centimeters. Now remember, femur length was our input, x, and height was our output, y. So if we have an x of 58 centimeters, how tall was that person when they were alive? So if you take that 58 centimeters and input it into your equation of best fit for x, you'll spit out the y value. So it would be 1.923 times 58 plus 80.681. So you should have about 192.2 centimeters. Is that an interpolation or an extrapolation? 58 centimeters is not within the original data set. 58 centimeters, this original data set had people that were between 50 and 39 centimeters tall. So this is outside of it. So this was an extrapolation. And so we don't trust it quite as much as an interpolation because it's outside of that. But it's not too far outside of it, so we trust it fairly well. If a person is 151 centimeters tall, what does the model predict for what their femur length must have been? So again, now we've got a y value, since their height was the y value, and we're trying to back into what the x value is. So now we set y equal to 151, and we solve for that x. So we 1.923 times x plus 80.681 equals 151. And when you crunch those numbers, you end up with somebody that is has a 36.57 centimeters long femur. Now, a person 151 centimeters tall is also outside of the original range. So that's an extrapolation as well. They didn't measure anybody 151 centimeters tall. So that was linear. You most likely will not encounter something quite so simple, but that was just to get us a little warmed up on how to do these. Let's look at the example number 2 for the curve of best fit. We've got a scooter store and their sales, and they're telling us, depending on what year it is, you can determine how many scooters they've sold. So they opened, and in their first year of business, they sold 15 scooters, and so on. So we're going to put this data into the calculator like we did before. And when we edit our data, if we had data in there before, let me show you how to clear it out. Toggle up to the L2, hit clear, enter. If you delete, that deletes the entire list. So we don't want to delete the entire list. We just want to clear the list. So then toggle up and over, clear, enter. And now we're ready to start entering our scooter data. So year 1, 2, 3, 4, 5, 6, and 7. And then we go over to the scooters they sold and make sure that we enter carefully. And I will show you how to do this in Desmos as well in a moment. So you've got our data entered. We want to look at our data. We have no idea what this data looks like. We can kind of see that it's growing, but in order to look at our data, we want to zoom in on the statistics themselves. And so when we zoom in our statistics, we say zoom 9. Oh, my apologies, I've got a function running in the background. Sorry about that. If you want to clear that out and have it not graph, we'll just clear your y equals so that you don't have that mess. So there's our data, and we can see that this looks like they're growing fairly quickly. They look like they're growing pretty exponentially on this one. Let's use our common sense and say we think they're growing exponentially, but also let's get our calculator to tell us how good an exponential fit is. Let's see if we like the R squared on an exponential fit. So we'll go to Stat and then Calc, and we will toggle down to exponential regression. And enter, 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 because everything is where we want it to be. And the calculator says an exponential regression has an R squared of 0.987, which is very, very good. It's even better than our linear regression from the last problem. And so we will take this exponential regression. It matches our understanding. It's certainly not a quadratic regression. It's not like the sales went very, very far down and then started climbing again. They only look like they were climbing. And so what this calculator is telling us is that the form y equals a times b to the power of x should be filled in with an a of 11.39 and a b of 1.451. And so that's the equation we will say is our curve of best fit. So our shape of our curve is an exponential growth. The equation we found is y equals 11.392 times 1.451 to the power of x. And please make note that when you are calculating things using this equation, you bring 1.451 to the power of x first, and then you multiply by the 11.392. Okay, so you can put a little multiplication in there to help you remember. Our coefficient of determination, the calculator said it was 0.988, which is a great fit. And now we're ready to answer questions that were outside of our original data set. So how many scooters will they probably sell in year 11? Year is x, so we'll input 11 in for x. So we'll bring 1.451 to the power of 11, and then multiply by 11.392. And we predict that they will have 684 scooters in that, or they will sell 684 scooters in that year. Now, since year 11 is outside the original range of years 1 through 7, that's certainly an extrapolation. Now, estimate the year in which they'll sell 300 scooters. To do this, this is very interesting. So to do this, we are going to use our table of values and also something called stow reg. to help us understand how to predict something in here, because we don't know how to solve for x yet. We haven't been taught how to solve for x when we have an exponential equation. We know how to solve for y, but we haven't been given the algebra skills to solve for x. So here's what we will do. When you run your regression, there's a step before you get to this point in which you can store your equation. So when you run stat calc exponential regression, hit exponential regression, toggle down to store regression equation. We want to store this equation. We don't just want to view it in that window. We want to store it in y1 so that we can use that y1 to build a table of values and to also draw our function over top of our data. To store it, have your blinker right next to store regression equation. Hit the vars or variables button. Go over to y variables, and we'll use number 1 for function y1. That's how you put y1 in here, and that's how you say, hey, when you're done calculating what the best curve of fit is for this, go ahead and store that in my y equals table. So we'll hit enter and we will calculate this regression, and once again it will spit it out in the format we are used to, but also notice that up here in y equals, it has also stored it there for us in a lot more decimal points than we would care to copy down. Most helpfully though, if we go second table, all of the x values and the corresponding y values, so all of the years and the corresponding sales projections, are in this table of values. So if we want to know the year in which they'll sell 300 scooters, we just toggle down. In year 8 they only sold 224, but in year 9, somewhere between year 8 and year 9, so within the year 8, they sold between 224 and 325, or we predict that they will. Okay? So we'll say in year 8, before year 9 happened, they sold 300 scooters. Year 8. So for your notes, store regression equation, that was vars or variables, y vars or y variables, function y1, if you want to store it in y1 and get a table of values. Okay? And once again, since this is outside the original range of data, this is an extrapolation, not an interpolation. Now I'm going to show you how to do this in Desmos as well, since that will be available in the SOL. In your Desmos graphing calculator, instead of typing y equals in this original line here, we are going to add a table. We're going to add a table of values, and just like we did in our calculator, we're going to add these values one by one. And I believe we don't need an 8, so we'll go over here to the y values and enter the scooter sales. And then in the next line, what you'll do is you will type the format of your function. Now, if you were going to try to fit a quadratic to this instead of an exponential, you would type it of the form y1, that's your output, y1 from your table, tilde, that's the top left on your keyboard, a x1, because that's your input, x1, x1 squared, plus b x1 squared, plus c. And that will spit out your fit, 0.998, your parameters, etc. Now we know that it doesn't make sense for these scooter sales to go down. It just wouldn't make sense for it to rise up and then plummet it down. So we know that it wasn't a quadratic fit, so we will instead put this of the form exponential. We'll say y1 tilde a times b to the power of x1. And that will spit out our A and our B values for our form. Okay, so you can not only do a table of values and make a curve fit in your calculator, you can also do it in Desmos. Just don't forget to use your subscripts, because your table is based on x sub 1 and y sub 1, as well as that tilde or that estimator instead of an equals sign. Okay? So if you would like, go ahead and pause the video and try your next question on your own. You can either use your calculator or you can use Desmos, depending on what you've got at home. Try a curve fit, take a look at your data first, use your common sense about this scenario, about Alex shooting free throws, and then we'll come back together after you've done pausing the video and take a look at the answers. So go ahead and try that. Alright, hopefully you were able to use your common sense and also look at your data when it was displayed and see that the shape of this curve was a parabola, an upside down parabola. Gravity is involved, you're throwing a ball, so we already were thinking that. And that your equation has y equals negative 0.11 x squared, etc. Definitely makes sense, right? It's an upside down parabola, so the a term should be a negative number. Your coefficient of determination turned out to be great. R squared turned out to be 0.958, so that's a great fit. When you input 10 into that equation for x, you should have gotten 13.547 feet. So the height of the ball when it's 10 feet from the free throw line, it should be 13.547 feet in the air. And this is an interpolation. They did, in fact, measure between 0 and 15 feet from the free throw line, and so that's an interpolation. Now, the distance from the free throw line when the ball is 9 feet above the floor, that's a y value, right? That's a y value. And when you calculated this, you could have done it a couple of different ways. One, you definitely could have stored that regression equation in your calculator and searched for the value when y was 9. You might not have been able to see exactly when that value was 9. Your table of values might not have gotten you there. And so you may actually have been subject to using the quadratic formula. You can use the quadratic formula. So if you have a quadratic and you know that y is 9, you input 9 for y, and you then subtract 9 from both sides so that you get 0 on this side, and the values of a, b, and c come out when the a stays the same, the b stays the same, and of course that becomes negative 4.785 there. And so when you do that, you've got x equals negative b plus and minus the square root of b squared minus 4ac over 2a. And of course you will have that available to you on quizzes and tests. So when you take those values and put them in there, you'll get the two values for x to determine which two x values get you a height of 9 feet above the floor. Now you will get two values. One of them will spit out a 15.23 feet. Well, that's past the hoop, right? When basketball, your hoop is only so far from the free throw line. It's 15 feet from the free throw line. And so that value of 15.23 feet, that's thrown out. And so we choose the remainder of the 2.67 foot answer, the second x value, and we use that to say that that is the answer for how far from the free throw line the ball is when it's 9 feet above the floor. Okay. Alright, so they are quite a bit of work within the calculator and calculations, but as long as you are careful about your data entry. Oh, and the last question, of course, this is an interpolation because we had data, and the 9 feet from the data that's something that we had already measured. Go ahead and try your homework and let us know if you have any questions, and definitely try to practice both the calculator as well as the Desmos.